Bon, donc on va pouvoir commencer la partie séminaire de cette séance. Et aujourd'hui, j'ai le grand plaisir d'accueillir Nicolas Regnault, qui est à Paris pour plusieurs jours. Et donc, Nicolas va nous parler d'un sujet qui est en plein développement, qui est la question des isolants fractionnaires, en particulier dans le contexte des matériaux de moirés, dont on parlera encore un petit peu plus dans les cours et séminaires suivants. Nicolas a commencé sa carrière en physique dans le domaine de la gravitation, et en particulier des questions d'intégrabilité en gravitation. Et puis ensuite, il a vu la lumière, il s'est tourné vers la physique de la matière condensée, en faisant un postdoc à l'École normale supérieure, je crois avec Thierry Jolicoeur. Oui. Je pense que c'est là où tu as commencé à t'intéresser à l'effet quantique.
Exactement.
Voilà. Ensuite, il est entré au CNRS. Et depuis
grâce à Hélène Boucher qui est dans l'audience. Voilà, une personne que je dois remercier pour être ici.
Bon, je te laisse la responsabilité de ça.
J'ai quand même fait un chèque de...
Depuis 2012 environ, il a été fortement impliqué et en partie délocalisé à Princeton, à l'université de Princeton, en particulier dans le cadre d'une collaboration extrêmement remarquable avec André Bernavik et son équipe, avec plein de papiers qui en ont résulté. Depuis 2 ans, Nicolas est chercheur au Flatiron Institute à New York. Et je ne vais pas faire la liste de ses faits d'armes en physique, juste mentionner qu'il est fellow de l'American Physical Society, qu'il a beaucoup travaillé sur les problèmes des folles quantiques et maintenant sur les problèmes de moirés, dont il va nous parler aujourd'hui. Nicolas.
Merci Antoine, merci pour l'invitation. So I will switch to English, unless you really want that I speak in French. But maybe actually better for you if I speak in English. All right, so the talk today is try to give you some perspective about what's going on in my materials, and especially realizing the analog of the fractional quantum Hall effect, but without the need of an external magnetic field. So let me, look back at the history of the topic of fractional chain insulators and how it emerged more than 10 years ago now. So the cool thing is it's part of this lecture on topological matter. So Antoine did already all the dirty job of introducing all the concepts, so I can go faster. But just in one slide, let me remind you how we can get the analog of a Landau level, but without a magnetic field. So this was introduced by Haldane back in '88, that only from the band structure, from the crystalline properties, you can have a band having a non-zero Chern number. And as you saw last week, if you have a non-zero Chern number, you have a Hall conductance. And that's the concept of a Chaire insulator. So it's basically insulator having at least one band with a non-zero Chern number. If I remember correctly, you saw 2 different versions of the Haldane model last week. This is another one called the BHZ model. Simple model, 2 orbitals per unit cell. So you have 2 bands, which are described here. That's the energy as a function of k x and ky. And as an exercise, just to see that you have quantum Hall physics emerging there, you can take this model and rather than considering periodic boundary conditions in both directions, you put your system on a cylinder. And you just diagonalize your Hamiltonian. And you will get the following structure, depending if you're in the topological phase. So you see that you have the bulk state in black for the valence band and the conduction band. And within the gap, you have the 2 edge modes. And if you look where they are localized in real space, you will see that one of the scarrow mode, like the blue one, is on the right side, whereas the red one is exponentially localized on the left side of the system. And if you tune a little bit, for example, the Haldane mass term, you can make your system trivial, and you don't have any edge mode anymore. And it took a few decades to have the actual experimental realization of a chain insulator back in 2013. This is a more recent experiment from people in Würzburg, where you see in red the whole resistance, and in black the whole the longitudinal resistance. As you see, you apply a small magnetic field because it's a magnetic system, so you have to define, like in a ferromagnet, to break the symmetry and either polarize in one direction or the other. And you see that zero field, well, you have a perfect quantization of the whole resistance and a zero of the longitudinal one, so which is what you expect from the chiral edge mode of the system. Antoine said I should speak Latin. My Latin is a bit rusty. I did that when I was young. But nothing comes out of nothing. So the idea of having the analog of the fractional quantum Morley effect without magnetic field, so coming from the lattice, directly from the lattice, is somehow an old question. You can trace it back to these two papers, one which is really looking at the fractional quantum Morley effect with a magnetic field plus the lattice by Cole and Reed. And another paper also by Laughlin that was trying to realize the analog of fractional quantum Morley effect, but using a spin system. So no magnetic field, just spin one, a bunch of spin 1/2. And it's also a lattice by construction. In the early 2000s, people in cold atoms were trying to realize the fractional quantum Morley effect. One thing about fractional quantum Morley effect is, this morning you saw how to build the Laughlin state for fermions, for electrons, but actually you have the same phenomenology for bosons. Remember the power m? Well, if m is even, then it's a symmetric wave function in a discrete bosonic system. So in principle, in cold atoms, if you have a strong enough repulsion between your atoms and you're able to mimic magnetic field, you should also observe the fractional quantum Morley effect. The problem is since your atoms are neutral, it's not easy to couple to magnetic field. So one option was to use optical lattices and realize the Hofstadter model. That's a numerical result from Gunnar Müller and Nigel Cooper in 2009, but it traced back to Afezi and Eugene Daimler in 2005. So from there, and motivated in the late 2000s by the boom of topological insulators, raised the question, can we have fractionalization if we include strong interaction in topological insulator? And of course, the simplest topological insulator that you can think about is a chain insulator. So several groups have proposed toy models where you numerically look at a lattice with a strong interaction, and you look for the signature of something that would look like the fractional quantum Morley effect. Now, let me give you a bit more details by using one example. Yet another model. This one has the benefits, so it's a Kagome model, just with nearest neighbor hopping, which is complex, right? And it works, so you can think about spinless particles. If you're a cold atom lover, you can realize, well, this kind of lattice has been realized a long time ago now. And once again, you have a single parameter, which is the phase of this hopping term. Because you have 3 atoms or 3 sites per unit cell, you have 3 bands. And you can show that these 3 bands will have a chain number 1, 0, and -1. And that's just the Hamiltonian, the Bloch-Hamiltonian for your system. Right, so you look at the band structure. It looks like this. It's already pretty neat, right? You could say, what's going on if I fractionally fill this band? But it's not, one ingredient when it comes to the fractional quantum Morley effect is the Landau level has 0 dispersion. So of course, if you have strong interaction, the interaction is the only energy scale if you project onto the lowest Landau level. But in a system like this one, you have a dispersion. So you have an interaction which is strong enough to basically overcome the dispersion of the band without inducing too much band mixing. So you want to be in a regime where your interaction strength is stronger than the dispersion, but weaker than the gap between 2 consecutive bands. But actually, you can do like we do for the fractional quantum wave problem. You can just project onto one band, which is like setting this gap to infinity. You can write down the model, so you can write down the Bloch Hamiltonian as a bunch of projectors, and basically you keep only the projector to the lowest band. Once again, the topology is in the wave function, not in the energy. So you will have the same, you preserve the topology, you just change the kinetic energy of your problem. Now you need to turn on some interaction. The simplest thing that you can picture is what Antoine has described this morning. You can think about the Haldane potentials. So you decompose your interaction into a bunch of numbers which correspond to the relative distance between your particles. And the shortest one you can picture for boson was this V1 pseudopotential. If you want to do that on lattice, well, if your electrons are spinless, you can have only at most one per site. So the shortest range interaction you can think about is just this density-density repulsion between two neighboring sites. If you want to do it for bosons, then bosons you can stack as many as you want on one site, then it's going to just be the Hubbard interaction. Right? So you have your setup, and what you do now is you put that in a computer like Lorentzian did in the early 80s and look for signature of fractional quantum Hall effect or the analog fractional quantum Hall effect. Okay, how do we do that? Remember the story of the quantum many-body problem. Simple stuff first. Spin 1/2. Let's say you have a bunch of them. You have, let's say, 2 states when you have 2 particles, 4 when you have 2, 8 when you have 3 particles, and so on. So basically, the size of the Hilbert space grows exponentially with the number of degrees of freedom you have in your problem. And just for a bunch of spin 1/2, if you have 1 terabyte of RAM, which these days is like having gold, because it's so expensive, you can do at most 36 spin 1/2, just to store the ground state, one eigenstate. Not talking about the Hamiltonian itself, just storing one eigenstate, decomposed into that basis. For the Lorentzian state, you can look at the amount of memory you need for the number of particles. And quickly you see that even if you have a supercomputer, you're basically stuck to 20 particles. So what should you do? Well, you can invest in a quantum computing startup, because that's why we would like to have a quantum computer to solve our problems. But realistically these days, maybe it's better to stick to just a cluster. And remember, more is different, but more is difficult. So how do we deal with that? You have different techniques you can use to really crack the quantum many-body problem for such a system. Remember, it's a strongly interacting one. So you cannot do like a perturbation of the interaction compared to the kinetic energy. You have to solve the problem at once. You can use exact diagonalization, which is I take a finite number of particles. That's exactly what Lorentzian did. You write down the Hamiltonian as a big matrix that you diagonalize, or at least you look at the low energy eigenstate. It's very versatile. It works in all the cases. The issue is the following. You're stuck to matrices which are typically like the size of 1 billion by 1 billion. After that, you're basically, whatever computing power you have, you're dead. You can use tensor networks. So tensor network is a very efficient way to encode many-body quantum state, and especially when this quantum state corresponds to a gap phase. You have basically an exponential gain compared to exact diagonalization. The other new kids in the block to try to tackle this problem is neural quantum state, which is just to write a variational state with 1 billion parameters that you have to optimize. The cool feature about all these fractional phases is that the correlation length is small. So namely, you have already lots of information when your system size is on the order of 10 electrons. Right? Remember, that's how you see that you don't need much. If you look at the gap on top of the Lorentzian state for the model interaction, you quickly converge, so up to some exponential small corrections. So you pick one of the methods. I will pick this one because I'm a simple person. I'm too dumb to use another technique. And you run your calculation, and you wonder, OK, how can I detect that have a fractional phase? So that will be the subject of the next lecture about topological degeneracy. As hinted by Antoine, the degeneracy of a topologically ordered phase depends on the surface where your particles live. So if you put them on a sphere, so a genus 0, for the Lorentzian state, you will have a single state separated by a gap from all the other higher energy excitations. If you work on a torus, the degeneracy will have a given number of states. So when you look at the Lorentzian states, at the fraction 1 over m, you have m states. In principle, the topological degeneracy is a property that you reach at the thermodynamic limit. So the degeneracy is exact only at large n. Fractional quantum Mole effect has way more symmetries. So for the fractional quantum Mole effect in a magnetic field, this degeneracy is actually exact infinite size. But it's a property of the magnetic translational algebra. So that's one signature. Usually, especially in a lattice system, it's not enough because you have competing phases that can also have a degeneracy of the ground state, like a charge density wave. So you have to look at the twist of the boundary condition, which is basically the flux insertion that Antoine was talking about. You can look at entanglement properties of the ground state because these are very specific entanglement signatures. You can look at overlap with model states. You can look at the spin polarization, especially when you're dealing with the actual realistic experimental system, because that's the first signature that you will aim at. Or you can try to do a mapping between fractional quantum Mole effect and fractional chain insulators. Let me give you an example of an energy spectrum. So that's the energy. Rather than doing like this 3D plot, I will plot the momentum this way. So kx plus nx, which is the number of unit cells in the x direction, times ky. So it's just to have one number to represent the 2D momentum. And as you see, for different system sizes, you can do the calculation, and you will have a threefold energy, almost threefold degenerate ground state. But once again, it's not enough to really claim that you have a Lorentzian state, because especially at 1/3, you can create a charge density wave which is commensurate and will be also gapped and have also a threefold degeneracy. So another signature that you can look at is looking at the excitations, because excitations is really at the heart of what make this fractional system special. So you have fractionalization of the charges, fractionalization of the statistics. You know how many excited quasi-Hall state you should get when you insert one flux or a bunch of fluxes in your system. You can predict that for the Lorentzian state. And so in this fractional chain insulator system, what you will do is also do look at the energy spectrum when you start inserting a bunch of additional flux quanta. Count how many states you have below the gap and check if the numbers actually match what you expect for the fractional state. Once again, the number here only depends on the statistics of the excitations. So that's nothing to do with if it comes from a magnetic field or just from the band structure. Antoine said that I should prepare an exam for you. So you can actually go there, and there is like a full tutorial to basically do all these calculations starting from scratch. So doing the time-binding model, computing the Chaire number numerically, building your exact diagonalization code, looking at the energy spectrum, and so on. So if you want, I will grade all your results. And please don't use AI for this one. I mean, you have to work. All right. At this stage, you might say, well, people have looked at many toy models, and most of the time, I mean, unless you're in very specific cases, you find fractional chain insulators. So basically, the reason is the following. As soon as you have one band, flattish, and once again, By flat, it's compared to the interaction strength. And so if it dominates the kinetic energy without adding too much band mixing, you will get such a state. So people have tried to put that on a more rigorous ground, knowing in which case a Chern band can be mapped exactly mathematically into a certain type of Landau level. So in the literature, it has different names. You find the name of ideal Chern bands, depending, who you talk to. So this especially was done at the Flatiron by Ji Wang and collaborators. Vortexable bands. Vortexable bands, it's a very nice idea because if you look at what you do, if you think about your Landau orbitals, you write them like this. You say, I have one state, so it's z to the m, exponential minus z squared over 4. And I can go basically from the orbital m to the orbital m plus 1 just by multiplying by z. Of course, if you think about a band itself and you have your Bloch state, multiplying by z doesn't mean anything. But you can attach basically a holomorphic structure, and this will basically exactly that, mimic this. It's like multiplying by z, that's what you saw this morning, it's like adding a vortex. That's the name of vortexability. And actually, all of this, you can reframe that in a slightly different way, saying that all ideal bands, vortexable bands, are just Landau levels, but in a non-uniform magnetic field, and potentially with a metric. That's it. These are very nice frameworks because they allow you to write analytical results when it comes to the quantum many-body states, like we do for the Non-Lorentzian state. But it's not a requirement. Most of the time models, like the one I've shown you about the Kagome, is not ideal. It's not a vortexable band. Still, you have a pretty nice fractional chain insulators. The reason behind that, all these properties are only about the one-body physics. FQH is about, of course, the topological band, but also interaction. And just by having some weird interaction, you can kill your state. The cool stuff, and that's why you can observe it experimentally, is that these fractional chain insulators are actually pretty robust, like all the fractional quantum Hall effect. That's why you see them in the experiments. And it's not only reproducing all we know in traditional Landau level. There are additional features for these FCIs. All right, so how do we realize them experimentally? And basically, the advent came from moiré materials. So just to go slowly, remember when it comes to flat bands, because a key feature of the Landau level is something which is, it has zero dispersion. Because of course the interactions are not very strong, so if you have dispersion is too large, you're basically dead. Flat band is about the energy. Topology is about the wave function. When it comes to flat bands, you have two main categories. You have flat bands that you can connect to an atomic band. So basically where you can adiabatically move your atoms in your system and keep your band flat. And you can you think about it as that you're able to exponentially localize. So if you take all your Bloch state of one band, you can recreate a basis which is exponentially localized in real space. So depending where the wave function is localized on top of the sides or in between, you will call that a flat obstructed atomic band or just a flat atomic band. But like this example here, which is the winding of the SSH wave function, once again, these two situations are not exactly identical. But the more interesting case is when you have actual topology, like a Chern number. Remember, a Chern number is an obstruction to create an exponentially localized basis. And if you try to localize, for example, if you have n unit cells with a Chern band, you can localize at most n minus 1, n minus c states. So topology is nice because it gives you basically, say that your electrons, they don't want to be localized. But now, as soon as you put interaction there, you know that something funny will happen because interaction will be the exact opposite. If it's a repulsive interaction, your electrons want to be as far as possible from each other. So people have tried to look for interesting topological flat bands in bulk materials. That's one more recent example where we have this database where you can try to find flat bands. But bulk materials are difficult to some extent. Like if you want to dope, something that you can do for the fractional thermal effect easily, that's the filling factor. You just tune your magnetic field. That's it. You're changing the filling factor. In a 3D bulk materials, you have to have dopant. So can we find something like a bit intermediate for that? Moiré, that's what we would need. So that's the origin of the term moiré. It's a French one, French name, as you can see by the accents. It's a nice fabric. It's also a nice village in France with a nice castle. They pay me each time I show this slide, so please enjoy it. But you've been there last week during the seminar of Dima Efetov. You can take a bunch of materials, like 2D layer materials, and start stacking them. So the most famous example is graphene. We can have twisted bilayer graphene that will create a moiré pattern. Another class of 2D material are the transition metal decalcogenite. So you have a transition metal and a chalcogen all together, forming this layer material. And depending if you have heterostructure or homostructure, you can play with the lattice mismatch between your two materials, or if they have the same, homo bilayer, for example, you can rotate one compared to the other and obtain this very nice moiré pattern here. And basically, the scale of these moiré superlattices, it's typically on the order of 10 nanometers. If you look TBG, twisted bilayer graphene, its magic can go, I think it's like 30 nanometers. We'll talk about twisted MOT2 as an example of twisted metal decalcogenide. It's on the order of 6 nanometers. So of course we would like to be there because the energy scales are way more important, so we get more stable. You can go the other route and basically look at longer system sizes. So basically that's what you have when you have cold atoms in a lattice. And really the beauty of moiré materials is their tunability. So you can do a simple exercise and wonder if I want to be able to dope a 2D materials, adding one electron at a time per unit cell, just by applying gates with a difference of voltage of 1 volt. What should be the size of the unit cell? Well, if you plug some more realistic numbers for dielectric constant, the typical moiré scale, as I said, it's like 10 nanometers. You can do the calculation for these capacitors and deduce what, if you have 1 volt, how many electrons you control per unit cell. And with these numbers, you will see that with 1 volt, if you have a moiré unit cell of 10 nanometers, you control 1 electron by 1 volt. If you wanted to do the same trick with just a monolayer, just having a bias of 1 volt, you will change by 10 to the minus 3 electrons per unit cell of the original monolayer. So there is no way you can dope with gates in this way a monolayer, but you can do it with a moiré superlattice. So that's really the beauty of these systems. You can dope, not chemically, but just electrostatically. So it was a long road toward the fractional theaters. You have different types of experiments that were using the moiré, but still using a magnetic field. So you have two examples of moiré pattern, one induced by a single layer of graphene on top of the boron nitride substrate. And basically you have a lattice mismatch, so that's why you have a moiré unit cell. And you also add a magnetic field, and what you realize is the analog of the Hofstadter model. Once again, if you plug the numbers, just as a reminder, the magnetic length is 26 nanometers per square root of B. So if you have a magnetic field of roughly 10 Tesla, once again, you're at around 10 nanometers, which is the size of a typical unit cell of this moiré system. You can repeat the same exercise for twisted biographene, and that's what people did. I think that's a group of Charlie Marcus, that's a group of Andrea Young. What they look here is they do a capacitance measurement, so they try to probe the bulk of the system to see if you have a gap. Remember, we talk about fractional quantum Morley effect. The ground state, you have a gap on top of the ground state, so in the bulk. So that's what you're looking at with this capacitance measurement. See, 2018, 2021, and now 3 years ago, two groups, one from Xiaodong Xu in University of Washington, and the group of Mack and Chen in Cornell, they have obtained, without magnetic field, a fractional transulator, a true fractional transulator, using twisted molybdenum telluride. But of course, capacitance measurement is only proving that you have a gap in the system. You're not proving that you have quantization of the whole conductance, which is really the hallmark you're looking for to claim that you have seen a fractional state. So these are the experiments. This is in the integer regime, so that's a picture of the device. They have their bilayer of twisted MOT2. You have the gates in graphene, you have the HBN substrate. It's cool because usually the system, you can not only control the density by the gates, but you can also apply like a voltage, a difference of chemical potential between the two layers. So you have actually an extra knob you can play with. And I will talk about that later when we talk about graphene. That's an integer case, a very nice quantization of the whole resistance at zero field. And now, if you look at the fractional case, this is the whole resistance. For the filling fraction minus 2/3, the minus is just because you're dealing with a valence band. And minus 3/5. Zero of the longitudinal resistance, quantization of the whole resistance. And which is also pretty surprising. If you look at this one, the integer case, people still sit up to 8 Kelvin. I think the fractional one, they can go up to 2 Kelvin. Remember that many of the experiments in gallium arsenide under magnetic field, so the usual fractional quantum Morley effect, you cool down your sample quite a lot. Many of the very, if you look at why we have so many fractions, it comes down to having very clean sample, and these samples are very dirty. Their mobility is like basically the same mobility that gallium arsenide back in the early 80s, and usually low temperature, like 10, 100 millikelvin. How can we understand these experimental results? Well, just a brief recap of what you did last week and that you will do next week, maybe, in more details. The case of twisted biography. So how do we model this? If you look at the moiré unit cell, we say it's like the order of magnitude is like 10 nanometers. The expert about graphene here can immediately spot how many, if you look at the typical distance between two atoms in a single layer of graphene, it's like 0.26 nanometers. Maybe, where is the expert? He left. Oh, he's here. You don't remember the numbers? Okay. But just to give you some idea, I think the number of carbon atoms that you have in a moiré unit cell at the magic angle, the order of magnitude is like 10,000. So there is no way, if in theoretical model, you want to deal with a tie binding model with 10,000 atoms. It's doable, people have done that in the past. But it's way more interesting to have an approximation. And 10,000 atoms, when you look at the scale of the moiré, it's like a continuum. So that's basically what Bitsos and McDonald did in the early 2010 to provide a continuum description of the moiré. And this is what I describe here. You have the two Brillouin zones of the actual layers of moiré, so the top layer in blue, the bottom layer in red, and you rotate the two layers, which will also rotate their Brillouin zone. And now the Brillouin zone of the moiré, which is, of course, it's much larger length scale. So much smaller in momentum space. It's this very small, tiny Brownian zone. And this is the dispersion of the single layer of graphene. And of course, what you will do is to simplify this dispersion by just looking at what's going on around the Fermi energy. So you replace the full dispersion by just the Dirac cones. You have one Dirac cone per K point of each layer. This Dirac cone is, of course, lives here in this Brownian zone, and now you have to fold it in this tiny Brownian zone. It's like folding it one at a time. And this is what you do if you fold the Dirac cone, and if you have some coupling between the layers, what you will do, unless you have symmetries, you will gap out anytime you have a crossing. And if you choose your angle wisely, you see that the band close to the Fermi energy will actually go flat. And this is what you get at the magic angle. I don't know if you have cold atom people in the room. So Jean Dalibard was working on something called optical flux lattices back in the early 2010-ish, I would say. Optical flux lattices are exactly this. It's exactly the same story, just in a very different language, but it's exactly the same calculations. What about twisted, the transition method decacogenide? So the model was also provided by McDonald a bit later, but it's exactly the same idea. Of course, the band structure of a single layer of twisted MOT2 is a bit more difficult than a Dirac cone. But what you will do is the following. You look close to the top of the valence band, and you will simplify this whole band structure by just saying, well, I have a parabolic dispersion. So you move away from the Dirac to go to the non-relativistic version. The simple Schrödinger equation describing a parabola here. These models have a very strong spin-orbit coupling. And the thing that is very cool is basically you lock the spin to the valley degree of freedom. So the two valleys that you have for this twisted TMD, which is hexagonal lattice, at the K, you can think about it's a spin up, and at K prime, it's a spin down. So you can really split your problem into looking only what's going on at around the K point, where you have the spin up, and the K prime when you have the spin down. Let's say I focus on the valley K, and I write the Hamiltonian. So here you have the kinetic energy for each layer, the top and the bottom layer. So we are basically describing the quadratic dispersion here. And if you look at the relaxation effect, they will actually induce two potentials, V plus and V minus, and you also have some coupling. And the rule of the game in all this business is to say, well, let's expand these potentials as harmonics. And the first thing that you will do is to truncate to the first harmonic, the simplest one. If you do that, these two potentials have this expression here. So you have a cosine. You have actually three parameters, the V, the psi, and the strength of the interlayer coupling W. So if you include the effective mass of the dispersion here, the simplest model you can think about for twisted TMD is only like 4 parameters. And once again, you have replaced a problem where you have typically on the order of 1,600 atoms per unit cell at the angle of 3.9 degrees to a simple 2x2 matrix with 4 parameters. So the question is, how do we get these parameters? And that's actually a non-trivial question. You can think about the kind of energy scales that are involved in the process. If you think about a single layer, if you look here, the energies are on the scale of the EV. Everything about moirés, you are on the scale of a few tenths millieV. So even if you do really careful ab initio calculation, they are very complex because of this difference of energy scale. 1 EV for the single layer versus 10 millieV for the moiré. And the relaxations play a very important role. And actually, if you want one application of machine learning to condensed matter, relaxation is done through machine learning because it's so complex that machine learning algorithm really boosts the speed of the convergence. People have tried different functional and so on, and at the end of the day, you have numerical simulations using ab initio This is if you assume that there is no relaxation in your problem without spin-orbit coupling, with spin-orbit coupling, and the full model with relaxation and spin-orbit coupling, which is the one that is closest to what you expect to have in the experiment, look like this. So you see that you have one top band, which is quite isolated from the rest. And what you can show is that this band has a non-zero Chern number. So if you think about the toy models I was showing, like the Kagome, of course, it's the valence band. So you think about holes, but it's the same story. You're on the right track. And you might say, why do we need such a, to do so fancy calculation to get the parameters right? Well, to be clear, having a non-zero Chern number for the top band is quite easy in the continuum model. You don't need to tweak a lot of the parameters. Now, if you want to look at what's going on for the remote bands, it's a bit more complicated. And like small changes of the parameters can actually change the topology of the remote bands. And it was a long debate in the community that was basically solved by the proper way, namely doing actual experiments that say that, well, at some angles, these two bands here should have opposite Chern numbers. Once again, just to maybe summarize, you start from your twisted MOT to you have a moiré, you have your DFT calculation from which you can extract parameters, and you have the continuum model. The continuum model, you can compute a Chern number, you have a Chern number 1. So to some extent, it's really like the Landau levels. And its interactions are strong enough compared to the dispersion here, we should get a fractional state. And that's basically why you have FCIs in twisted MOT too. This is a summary of all the experimental results when it comes to all the fractions that have been observed, all the phases that have been observed in twisted MOT2 as a function of the filling factor. So once again, minus signs just because you're dealing with the valence band, as a function of the twist angle. You have, of course, a very robust quantum anomalous state, so a Chern oscillator. And you have a very nice FCI. The strongest one is at minus 2/3. And if you use the proper calculations, numerical calculations, but first to extract the parameters, and then to really take into account effects like band mixing and so on, you can try to reproduce this phase diagram for the different filling factors as a function of twist angle, and see in which case your model predicts an FCI or not. Something very funny is there is a strong asymmetry in most of these systems, between minus 2/3 and 1/3. So it's very rare to find an FCI at minus 1/3. Whereas if you remember maybe the picture that Antoine flashed about the fractional quantum Mole effect, you have like a particle symmetry within a Landau level. So if you have a fraction at 1/3, you expect to have a fraction at 2/3. If you have a fraction at 2/5, you expect to have one at 3/5. This system doesn't have the particle hole symmetry. So that's, for example, one of the big differences with a typical Landau level. Let's talk about other differences. There are, for example, now we are at the stage where experimentally you can extract the gap, the transport gap, for these fractional phases, like people have done for fractional quantum effect. And the gap structure is a bit more complex. Basically, if you look, what you expect if you have only the fractional quantum Mole states, like 1/3, you expect the longitudinal resistance not to be strictly 0, but actually to decrease exponentially. It's an Arrhenius law with the temperature. And when you do that for an FCI, you actually find two gaps. And you can basically tune these two gaps by changing by adding some additional magnetic field. And you can reproduce some of these results with using numerical simulations. So, and another property which is different from Landau level, as I hinted previously, the topological degeneracy is exact when you work in a Landau level because you have extra symmetries. These symmetries will imply, for example, that your anions don't have a dispersion. They are dispersionless. But it's not specific it's not something that emerged from the fractional charges or fractional statistics. It depends on the microscopic details. As soon as you move away from a Landau level, this will break down, and your anions, so here, let me think carefully, that's for the quasi-electron and the quasi-hole, and you see that they have a dispersion with some nice symmetry properties and that you can explain that also related to the fractional statistics and the fractional charges, but let's talk about that later. You can look also at the spin, the magnetic properties. So one thing I didn't mention, or I was talking about that when we discussed the first observation of a chain insulator back in 2013, these are magnetic materials. So what you do usually is you apply very small, it's a ferromagnet. So what you do is you apply a small field to tilt your, to favor one direction or the other. But the spin structure is quite different from a fractional quantum Hall effect. Usually fractional quantum effect, the main description, we forget about the spin degree of freedom. But you think of nu equal to 1, you have a spin, and there is a very nice physics emerging there because you have SU symmetry, you can talk about skirmions and so on. Here you don't have SU2 symmetry. As I said, K and K prime lock the spin, so valet K, you have one type of fermions in the moiré with the spin up, the other one with the spin down, but you only have a U1 symmetry. You don't have the full SU2. So you have Ising magnetism compared to Heisenberg, and you can look, for example, at excitations, they will be gapped. You can build Magnum state. You can do that for the integer case, and you can do that for the fractional case. So that's yet another difference between Landau level and these chain insulators. At this stage, we have a complete family picture, right? Starting from 80, the quantum Hall effect, the integer case, 82, the fractional case. So you will see there's a question of terminology, whether you call it anomalous quantum Hall effect or chain insulator. Choose your religion. It's not my problem. 2013, the first observation of the quantum anomalous Hall effect, and like 10 years later, the fractional one in moiré system. Since 2023, we had a bunch of papers, so people have explored a lot in the system, see the difference between these FCIs and the fractional quantum Hall state. So which raises some questions like, what are the future directions for MOT2 or for these twisted TMDs? It's really going beyond Landau level physics. Remember, we don't have a magnetic field. So one cool stuff is we can have superconductivity and your fractional state. So technically, to be honest, fractional quantum effect, you can have superconducting contacts. I think niobium is one of the superconductors that has a very high critical field, but they are very dirty in terms of contact. So now you can do really cleaner stuff to put in contact these two systems. And there's lots of interesting physics that could potentially emerge at the boundary between a superconductor and a fractional phase. And it's not science fiction. So that's the group of Sengfeng Wu in Princeton. He has already realized some of these interfaces between twisted MOT2 and a superconductor. And actually, you don't even need to have to add a superconductor by hand. There are some recent results from the group of Ting-Sing Li in Shanghai, where if you look at the resistance, let me check. I think that's the whole resistance in red, and the notional resistance in black. And there is a region which is quite in the vicinity of, so that's the filling factor 2/3 here. In the vicinity, you have both a vanishing of the longitudinal resistance and the Hall resistance. So it's not direct, it's not a strong evidence. You cannot claim technically that superconductivity because there are cases where you can have similar signature, but it's a first indication that there might be some. And there's lots of interesting questions because what is the nature of the superconductivity? So if you look, there are proposals in theoretical proposals that say, well, since my anions now have dispersion, but I also have residual interactions, I can play the same game. It's just I can have superconductivity from anions. It's actually not a very new story. It was proposed by Laughlin decades ago, but it has a new interest potential in this system. Another phase that you would like to realize is fractional topological insulators. So a fractionalization, but without breaking the time reversal symmetry. Chain oscillators break time reversal symmetry. You would like to get the same kind of physics without breaking it. Right? So it was predicted like in the early 2010 also. There are still no strong experimental signatures, but there are some interesting features at -4/3 that might hint toward this phase. And the reason people are really excited is because if you combine superconductivity and these fractional topology constitutors, you have generalization of the Majoranas. So, Majorana has been elusive for a very long time, so you can double down and get something even more exotic by combining them. Okay. But for now, what I did was to say, I have a band with a non-zero Chern number that looks like a Landau level. It has a gap. It's almost flat. And I get something fractional. But that's not the end of the story. So like 3 months after the MOT2 paper, there was another system that was exhibiting fractional chain insulators, and it's rhomboidal graphene. And it's really hell when it comes to the theory. And I will show you why. But from the experimental point of view, it's a very clean system. They seem like, large number of fractions for the first few samples. So rhomboidal graphene, it's like several stacks of graphene where you have the Bernoulli stacking, so A on top of B and so on. And you have 2 HBN substrate. And what you do is to align one of, let's say, the bottom of your, here in this picture, it's the top. Later I will use the bottom, sorry for that. You slightly align the HBN and you rotate it. So you induce basically a moiré from the HBN and the top layer of this rhomboidal graphene, not the bottom one. And if you do that, you will also observe in these transport measurements signature of fractional chain insulators. It's been done in pentalayer graphene, so 5 layers, but also in 6 layers, same physics. I'm not sure if there's for 4, there might be some, but people have never seen anything for 3 and 2 layers. So as I said, you need some moiré that comes from the boron nitride substrate. And here it's a picture of the Brouillard zone. So you don't have the same lattice constant for boron nitride and for the graphene. So not only you have a mismatch of the 2 Brouillard zones, but on top of that you rotate them, but you still generate this very nice moiré pattern. Typical angle is around 0.7 degrees. I mentioned previously that you have an extra knob. So not only when you have your 2 gates, you control the density, so you control the doping in your sample, but you can also apply an additional electric field. So you can, for example, push the electron to the top or the bottom of your system, depending on the sign of your displacement field. And if you can do like a simple model for this structure here, including with the boron nitride substrate, and you will get a band structure like this one. Basically, the gap here is controlled by the displacement field. And if you look at the conduction electrons, you do have a flat band, but there is no gap. And actually, it's worse than that. It's not a Chern band one. So it's definitely not like an endo level. So first question, where are the electrons? So that's why I said that I flipped now the moiré is at the bottom, and I have my displacement field. So depending on the side of the displacement field and whether I look at electrons or hole doping, in one region I have fractional states. It's called the moiré distance. So the actual electrons that you contribute to the transport are here far from the moiré. And still, you obtain fractional states. You can look at the other situations. There are potentially also fractional states appearing in I think that's the moiré proximal case. So this one. Yep. So where are the electrons? Far from the moiré. So next question is, what does the moiré actually do in your problem? It's actually tightly related to the way you think about the interaction between the electrons in the system and how you deal with it in practically as a theorist. You can think about what you do when you have a semiconductor, if you have a large gap. Let's say you look at the conduction electrons, and usually if you have a large gap, you say, well, I don't care about the valence band, right? Of course, this is not the same statement if you have Dirac electrons, because there is no gap. So you have to properly take into account the effect of the field valence band. And the question here is basically what is the strength of the interaction compared to the gap that you have in your system. If you're in a regime where you really forget what's going on about the valence band, then the moiré doesn't play any role. Remember, the moiré is from the electrons that are far away from the HB and substrate that is aligned with your rhombohedral graphene. So it should be like you should need a mechanism that will spontaneously break the translation symmetry to give you some moiré. And that's the whole business of the anomalous Hall crystal that was developed in with Flatiron or in the Boston area. The other approach is, no, we cannot neglect the electrons that are here. And basically, if you do like some kind of Hartree-Fock treatment, if you look especially at the density profile of the field valence band, because they are, especially these states here, are very close to the moiré, they have the imprint of the moiré potential. So you can try to do some simple Hartree-Fock calculation in these two kind of regimes. Both cases, depending on the parameters, will turn this gapless conduction bands into a very nice gapped one with a Chern number 1. And you can say, well, I got this from Hartree-Fock, but still I can forget about this band and start thinking about doing fractionally filling them, doing some ED calculation, and whatever you do, basically, for the filling factor 1/3 or 2/3, irrespective of the number of particles, you have very nice FCI in numerics. Problem is, 1/3 is not observed in experiments. And maybe I should point out that as soon as you start moving away from this picture here, like for actually including all the bands, everything breaks loose. You don't get any FCI. So we were a bit stuck and as a community to explain exactly what's going on. And I will try to, once again, let's go back to the experimental results, and especially the new ones. So the question is the moiré crucial? If it's spontaneous symmetry breaking, it should not matter much. I think now from the experiments, we are exactly convinced of the opposite. Moiré is crucial for all these phases. So this is some result from the group of Xiaobo Lu in Peking, at Peking University, where basically he was able to change the twist angle, and you can see a very strong effect. I mean, you have like not even a fractional one, just Chern insulator will appear or not depending on the twist angle. And clearly, as soon as you have a trivial phase, there is no FCI. So if your twist angle gives you a trivial phase at interfilling, there is no FCI. If you have one, then potentially at 2/3 you get some state. And once again, if you take this model and you use Hartree-Fock to try to describe the experimental result, it fails miserably. If you do something a bit more careful, you actually have something that is more in line with the experiment. So that's one example where the Hartree-Fock actually fails. So that's one thrust of evidence of the importance of moiré. You can also think about the more recent experiment of the group of Longju at MIT. So here's the one I did the first experiment on rhombohedral graphene showing that you have fractional Chern insulators. If you have moiré, you have anomalous crystal, anomalous Hall effect, you have fractional Chern insulators. If you don't align, you have superconductivity. Different physics depending on not if the moiré is there. So with this, I think it's pretty convincing that the moiré is crucial. So one thing that we did was to try to model it a bit more properly. So without entering too much into the details, the actual full Hamiltonian for the model is quite nasty. So you have lots of terms, the rhombohedral graphene, the coupling with the boron nitride substrate, the potential created by the displacement field, and of course in the interaction that you handle by also taking into account the effect of the field valence band. And you can simplify it by having some effective non-interacting Hamiltonian that basically include the effect of this, what we call the moiré capacitor, because basically the field band acts like, give you electrostatically the moiré on the conduction band, even though the conduction bands are far away from the actual physical moiré. And you have your interaction properly normal ordered, so and you can do your calculation. It was kind of a bit of, epic battle in terms of numerics, because you want to show that if you include all the bands and you do a calculation properly, that you try to treat more precisely the effect of the field valence band, you do get an FCI. Forget about all the glory details of these plots, just tell you how we do some, we handle the actual Hilbert space. But the plot that is important is here. It's the gap as a function of the truncation parameters to allow us to do the calculation. And whatever we do, we have a gap, which is finite, on top of a fractional state. And the very funny stuff is, if you look at the nature of this fractional chain insulators, it has, of course, the same universal properties. Fractional charges, the charge E over 3 or 2 over 3, depending on the filling factor. You have fractional statistics. But it's not made out of one band. You can look, for example, at the density as a function of K for your ground state. And so the blue, red, and green, it's just the occupation of the remote band. And you see that you have quite a substantial occupation of the remote band. And it's not a matter of choosing like a basis. Whatever basis you choose, you always have some mixing. And it's actually even more funny than that. If you take your system, but you don't include the band mixing, what you get is a Charles-T wave. So you get the wrong physics. So once again, that's something that is a clear departure from the cartoon picture I was showing at the very beginning of field, a churn band that you fractionally fill with interaction. All right, so I think I'm on time. I would like to thank many people that I've worked with on this topic over the last few years. And especially some not young anymore, Yves Kwan and Jabin Yu, our faculties in the US, but also Jonah Herzog-Arbeitman, that just graduated from Princeton. H. Lee was a postdoc with us, and Andreas Feuerpfeil, and lots of people that you can find here. And as a conclusion, it's really an exciting time for all this physics. Remember, like 10 years ago, it was just a theoretical prediction or nice toy models in a computer. Now, thanks to the advance of moiré, this is actually something that you measure in experiments. And as usual, the experiments are a bit more interesting than the toy models. The physics is a bit more complex. We have more things to understand. And I've shown you, the case of twisted mode 2, that is the nicest case, but they are not all like this. And even the details do matter, like the nature, the excitation, the magnetic excitations, the possibility of superconductivity in the system. This is a stuff that's still to explore and understand. So I hope that will motivate the young people to have a look. And maybe if you're interested, you have to do the homework, and we can talk about it. Thank you.